Okay, now I want to show you how you can use performance-based earthquake evaluation method to assess the relative benefits of different structural systems. This work I performed together, or this was supervised by Professor Mehan, and I had a student helping me on this. It's like Sean Merrifield. The earthquake engineers, they're generally trying, when designing the new buildings, they're generally trying to accomplish two tasks. They try to preserve life safety, and they try to prevent collapse. However, each new earthquakes brings new collapses. And from each new collapse, we try to learn something new, and we try to improve codes so we don't see this anymore. If you look in the but still, if you look at the building codes, you'll see what is the requirements that they're putting on you. They want you to safeguard against major structural failures and loss of life, but they do not limit damage, or they're not concerned in maintaining the function of a building after an earthquake. And this is similar to what we have in the car industry. So when they're testing the car, the only concern that they have is to preserve the life of a human being inside the car. And car is pretty inexpensive compared to the building. So after an accident, the car is dumped, it's recycled, you buy a new car and you move on. But with earthquakes and buildings, after they're extensively damaged in an earthquake, it's really hard to repair. Although they preserve lives and there is no real collapse, it's really hard to repair them and bring them back to the original function that they had before the earthquake. Also, non-structural elements threaten life safety, and the damage that they cause is really disruptive and expensive. And as structural engineers, we don't really think much about the non-structural elements when designing new buildings. So to look this from a different perspective, there is this holistic risk-oriented view, which is called performance-based seismic design, where you rather of just preserving the safety and preventing collapse, you also try to minimize the losses that your structure will have at the end or after an earthquake. And basically, you do this loss analysis, and you can fulfill different requirements when you're doing loss analysis. You can look at the losses in terms of money. You can look at the downtime of the building for an earthquake. You can try to minimize these. You can look at casualties and so on. And someone may get scared when they see the whole like this procedure of going through in order to calculate losses, but it's not that difficult. So basically what you do, you start with creating the hazard model of your site, and using the hazard model of the site, you then come up with a set of ground motions that you use to run your structural system to get a structural response. Then you relate the structural response to the damage, and for this you use fragility curves. And then you relate damage of the components of your system with the consequence functions that actually tell you how much this damage cost. And then you integrate over all components of your system to see what is the final consequence, what is the final loss of your structure going through an earthquake. And you can do this for one hazard, or like for several hazard levels. So one by one, and you can look at the losses for each hazard, and then also you can integrate over all different hazards and get some annual losses or life cycle losses of your building. So we think it's better if you consider performance from three perspectives. If you look at structural response, if you look at losses caused by scenario events, and if you look at expected life cycle losses, costs, then if you only are concerned with the structural response, which is common practice in structural engineering. So in order to show an example of how this can be done and what are the benefits of doing PBEE analysis, we looked at different structural systems. These are all 3-story steel office buildings that is located in Oakland, in California, on a soil type D. And basically, we tried for the start to try to compare 2 structural systems. First one is like just conventional special moment resisting frame, but then we wanted to improve seismic performance of the system. So what we did, we base isolated it, and after we base isolated the structure, we kind of looked at 4 different alterations of the design of these base isolated structures. So we looked at 2 different bearing designs, and we looked at 2 different superstructure designs. Special moment resisting frame and base isolated frame that we called baseline case are both designed based on minimum code requirements. The other 3 isolated cases are some improvements where you invest a little bit more money to improve structural response and to improve the losses or to reduce the losses. So what we did, we have the first case, which is baseline case. This is minimum code design. And then we improved the design of the isolators by reducing the forces that are going to enter the structure like twice for both DBE and MC level. And then we kept the original design of the isolator system, but we improved the superstructure by doubling stiffness and strength. And basically, with these 2 options, we are going to try. We try to achieve the same. Either increase the stiffness and strength of the structure twice, or reduce the input that goes in the structure twice. So basically, you're going to achieve the same. And then the last or the 4th option here is let's improve both isolators and superstructure. And in loss analysis, to assess effectiveness of these designs or the improvements of conventional designs, we looked at business downtime, and we looked at financial losses that were total financial losses that included repair cost and loss in revenue due to business interruption. And we performed 2 types of assessments. We look at scenario-based or hazard-based assessments, and we looked at time-based assessments where we basically look at the annualized losses. This is something that insurance companies like to see. And we look at the return on investments by improving the structural systems. To do the cash flow analysis to come up with the return on investment, we need to look at the initial construction cost of each system. And here I'm showing first for the special moment resisting frame, and next I'm showing for the 4 isolated systems. And in red, I'm showing the net increase in cost due to isolation or improving the isolation for these 3 cases. And you see, if you look what is the percentage or the net increase in cost due to isolation of the system, you see it's like a really small percentage relative to the total cost. It's maybe in the range of 4 to 8%. However, in industry, it's a little bit different. When developer comes to you and wants you or asks you to give him some options of a design and to estimate the cost of a design, they only look at the structural portion of the cost within the total construction cost. And if you tell them, yeah, if I put isolators, your cost is going to increase 25%, but you will reduce the losses later on and you tell them what is the return on investment by investing this 25% in your structure, or maybe 4% over the total expense, they may start thinking differently than what they think at the moment. So let me now go through the methodology, through the whole process of coming up with the values that we are interested in. So first, I want to say this is downtown Oakland. This is the location that we looked at, and it's about 70 kilometers away from the hazard fault. So first you need to develop your hazard model for the site. And you can use the aggregation of the site to see what are the possible earthquakes and their contributions to the site. And then based on this, you can decide at how many different hazards or scenarios do you want to consider in your analysis. So for this particular analysis, we looked at 3 different scenarios. We looked at something which is commonly called frequent earthquakes with a return period of 72 years. We looked at the design basis earthquake, and we looked at the really rare earthquakes that are high in magnitude. And here I'm showing you in the black line, solid black line, I'm showing you acceleration response spectrum at dB level, and with the blue and red lines, I'm showing you the mean of the ground motions that we considered in this study. There were like 40 ground motions at each hazard level, and with the dashed line, I'm showing you the same for the maximum credible event, which is MC level. So to develop the structural model, we need to look at the geometry of the building, and we need to look at the possible. We have to go through the whole design process before we really analyze it and do PBEE analysis. So here I'm just showing you the outline of the building. It is like a 6x4 bay. Lateral load resisting systems are at the perimeter of the building. Bay spacing is 30 feet, and the story height is 15 feet. And here I'm showing you 3 basically superstructures, or like structural systems that we looked at. The first one is special moment resisting frame. Then the bays are isolated with the first type of superstructure, and these 2 are the minimum code systems. They satisfy minimum code requirements, and this one is the improved system compared to this one. So previously I said that we looked at 2 types of isolators, or 2 different designs for isolators. For the study, we used triple friction pendulum bearings, and here I'm showing you the curves, hysteretic curves for these 2 bearings. With blue, I'm showing you the minimum code design, and with the red one, I'm showing you the improved design by keeping the effective damping on the bearing same. We increase the effective period of the bearings to reduce the forces 2 times at both DBE and MC level. So now that we know geometry and we have a design of the buildings, and we know our bearings, now we can proceed and do the analysis. Of course, analysis is performed with OpenSees. And to simplify the problem, because like for the PBEE analysis, you need to do like lots of runs, we decided to simplify our model. So instead of looking at the 3D structure, we looked only at the 2D frames. The loads that we applied were gravity loads, and then for the earthquake, we considered vertical and horizontal component of excitation. To account for P delta effects from the gravity columns, we modeled the leaning column. Beams and columns we modeled with nonlinear force-based beam column elements with fiber sections, and with low cycle fatigue failure capabilities. All elements for base isolated and for special moment resisting frames, they all use this element, except of beams of special moment resisting frames that had like reduced beam section connections. We couldn't use force-based beam column element on this one because the section is not uniform. These are like not uniform over the length. It's reduced. So what we did here, we modeled the beams with reduced beam sections using rotational spring, elastic element, rotational spring assembly. And this is like basically concentrated plasticity model with the rotational hinges at the element ends. Isolators, we modeled with the zero length elements and trilinear model. So in zero length elements, we only assigned horizontal springs to represent the isolators. Panel zone regions, we modeled with elastic elements based on recommendations from ATC 72. We accounted for geometric nonlinearity utilizing p-delta transformation. And damping model is something that is really, really important to carefully consider when defining your model. And we spent like some considerable amount of time in creating the damping model for the systems. We decided to go with the damping ratio of 3%. We found this to show, like, we looked at different reports, experimental results to come up with a reasonable value for damping ratio. And for the special moment resisting frame, we went with the Rayleigh damping that was mass and tangent stiffness proportional, where at frequent level earthquakes, it was based on the first and the third period, and on the DBE, which is design based, and maximum credible earthquake, which are rare earthquakes, we had like, it was based on 1.5 times the first period and the third period. This 1.5 comes from elongation of period within the system due to all nonlinearities that happen into the system for these stronger earthquakes. In case of isolated systems, we use only tangent stiffness proportional Rayleigh damping model. Why we didn't account for mass? Because some studies have shown that rigid motions, such base isolation systems, show if you account for if you add mass damping into your model, it really increases the damping of the structure greatly due to this rigid body motion of your superstructure. So we found recommendations of not really using mass proportional damping within the base isolated structure. So after we performed the analysis, and just before I show you the results, I want to say that I could do, like with one click, so now a little bit about OpenSees. So I created the file, the whole script, where I did the analysis at all these 3 different hazard levels. And total, I had 240 runs. And it could do it in maybe 4 hours. All these 240 runs for 3 different hazard levels. And I think it's impressive. And like, I would run it after I go home, and in the morning I'll have all results and being able to look at and analyze them. So let me now show you the median Storey drifts. So here we see that the base isolated that has improved both superstructure and isolators, of course, has the smallest drifts because it's the most robust out of these 4 isolated buildings that we looked at. And then the 2 isolated buildings, one that has improved isolators and the other one that had improved superstructure, they have the same response. And if you look along these 3 different hazard levels, you see that these 2 lines are always at the top of each other. So we achieve the same things either by improving the isolator or by improving the superstructure. And then for 50% in 50-year earthquake event, we have the isolated system, which is designed based on the code minimum to give you almost the same drift response as the special moment resisting frame. So here we didn't see much of contribution or like improvement in the performance by isolating the structure. If you move to next hazard level, which is design basis earthquake level, we see that the drifts of the three improved isolated system did not change much from what the increase is not that big from what they were at the 50% in 50 years, but the other two systems have like somewhat larger drifts, and now like as a good thing we have some separation between the isolated system response and the special moment frame response. If you look at the maximum credible event hazard level, we see that the 1% drift level is like commonly where the yielding occurs. So all of these three improved systems, actually none of them yielded at the maximum credible event, which is amazing, I think. While the base isolated frame based on code design had the yielding at all three stories, and the special moment resisting frame had a drift close to 3%, which is close to damage level, first damage level for the RBS connection, which is lateral torsional buckling, but it was far away from the failure, which happens at 5%. So now if you look what we were able to achieve by improving performance of the structural system through introducing the base isolation, we see that for each hazard level there is a huge reduction in drifts, and this is especially observed for the improved systems. We see that there is a really small improvement from special moment resisting frame if you look at the base isolated frame that is based on code minimum. So if you just improve it a little bit, you have a little bit better, you have somewhat better response. So next, if you look at accelerations, along three different hazard levels, picture looks almost the same. You have like special moment resisting frame that has the highest accelerations, floor accelerations, and you see at all levels, hazard levels, you have the increase in accelerations along the height of the structure. By base isolating them, we reduce these accelerations significantly, and doesn't really matter what is the superstructure. Based on the design of the isolators, we reduce them to a certain extent. So we see that this line is if we use like based code isolators, but if we improve the isolators, we achieve a little bit more reduction in the acceleration response. And another thing that it can be observed for all these three different hazard levels is that the accelerations along the height of the structure are somewhat uniform. We don't see that much increase along the height. Then if you look how much reduction in acceleration response did we get by introducing the base isolation, we see that all four isolation systems are really good, and it's somewhat consistent through all three hazard levels. It's about 70% if you use like the code-based superstructure, isolator system, but we improve the isolation system, then it's about 83%, and it's like almost the same at all three hazard levels. So then we can summarize the structural response. Special moment resisting frame has a relatively large drifts at all levels of excitations. We see that yielding starts at design base earthquake hazard level, And non-structural damage is triggered at 50% in 50 years. At the frequent earthquakes, we have like non-structural damage. Accelerations are also large at all levels of excitation. And again, non-structural damage of acceleration-sensitive components within the structural system is triggered at the frequency level events. And another bad thing is this amplification of acceleration along the height. So if we move from this one to the code-based, base-isolated system, we managed to somewhat reduce the drifts. It's not impressive, but it's better than it was in case of special moment resisting frame. Here we move the yielding to the maximum credible event. And again, even here, the non-structural damage is triggered at 50% in 50 years, same as what we had before. But if you look at accelerations, here we have a benefit of using the isolators. We reduce them 70%, and they're almost uniform along the height. And with this, we do not cause any damage to the acceleration-sensitive components of our structural of the structure. So next, if we improve the isolators, then we see significant reduction in drifts. There is no yielding at all. Non-structural damage happens at the dB level. Accelerations are really, really low. Non-structural damage is not triggered, and they have uniform acceleration along the height. Similar thing or similar response is observed if we improve the superstructure. And then, of course, the best response we see if we improve both isolator and superstructure. And based on this, we can try to grade our structural systems. So I would give 4 stars to the system where we improved both isolators and superstructure. And then I'll give maybe 3.5 to the system where we improved superstructure. And I'll give maybe 3 3/4 to the system where we improved the isolator. Minimum code designed isolator system would get 2 stars because it has poor reduction in drifts, and it triggers non-structural damage at like frequent earthquakes, which is not good. And special moment resisting frame is just 0. Like, it's not good. And as I mentioned before, now it's time to, after we perform the analysis, now it's time to see what are the losses and to compare them for all these different structural systems. So first I'll start with hazard-based assessments. To perform this analysis, we used PACT 2 software, which can calculate repair costs for each hazard level of all components of your system and the total repair cost. And it can give you the repair time of each damaged component. It also has a way of calculating the total repair time, but it's not really good, and we did not like it because for one floor level, you have option to either repair all of your components in parallel, all of your components in series, which is not really realistic, and it's not how it's done. So we didn't use that capability of PACT. Instead, we developed our own method on calculating the repair time. And in addition to looking at the repair time, we looked at the mobilization time, which may cause business interruption of a structural system. And these mobilization factors are building inspection, permitting, financing, and so on. So just a small introduction into PACT. It is a FEMA ATC 58 product, which is based on PBEE methodology. Here, modeling process is broken into 3 stages. It's pretty simple to use. It is straightforward. You provide building information, then you define structural and non-structural components, and you provide the content of your building, and you include quantities for each of the component. Then, based on your structural analysis, you provide the EDPs, which are the responses of your system. And what they take are interstory drifts, floor accelerations, and residual drifts. So you provide this input. You provide this as an input into PACT. And then what PACT does for you, it solves this relationship from structural response. It calculates the damage using fragility curves that are built into PACT, and then from then on, for each damage state, it calculates the cost of the repair for that damage, and it integrates over all components and gives you the total repair cost of a system. It also uses, I just want to point out that it uses Monte Carlo method to take into account the uncertainties within the modeling process, such as component quantities, loss assessments, and so on. And now I'll try to quickly show you the results. So at the frequent earthquakes, here again I'm first always showing the special moment resisting frame, and it gives you, I'm showing the median loss, which is here given as a function of the repair cost. I'm showing the median and 90% loss. Next I'm showing the code-based, base-isolated system, and then I'm showing the 3 improvements that we did on the isolation system. And you see that by isolating the structure and confining to the building code, you reduce the costs like about 2 to 3 times. But then by small improvements that are pretty inexpensive, you really reduce it down maybe like 5 to 10 times. And capability of PACT is to also give you the contributions of all components that are damaged within your system for each hazard level. And it's good to see like if you can fix something within your model to prevent this type of damages that you see here. And so now I'm just going to show you, like, compare different systems to show you how much damage each one of them has. So basically, if you have lots of them, it means it's not good. Too many components are damaged. If you have just few of them, it's better. So if you looked at the code-based isolated system, now you see that there are only few damages, few components get damaged. And if I look at one of the improvements, it's again few. And this is all given as a percentage of the total loss. So if you look at the design basis earthquake level, the trends are the same. You have significant reduction just by isolators, and then by some small fixes of your building or tweaks, moving a little bit beyond the minimum code design, you reduce the losses greatly. And again, here you see that the design basis earthquake, lots of components get damaged within a special moment resisting frame. If you go to the code-based isolated frame, situation is better. You have fewer number of components. If you go to the improved system, it's even better. At the maximum credible earthquake event, these are rare earthquakes. Here you don't see that big advantage of isolators. This difference is not that big, especially if you look at 90% confidence level. And then if you look at these 3 systems that are improvements within a base isolation system, if you look at the median, the trend is good. But if you look at 90%, you see that there is something not so good with the system that has improved isolators. And again, now you see, like, for the maximum credible earthquake, many more components within the system get damaged. And I want to point out that like about 20% of the total damage comes from the structural components. Everything else is non-structural. If you move to the isolated system, we again see like many components getting damaged. And again, I feel like 20% of the cost goes to the repair of structural components, and the rest goes to the repair of the non-structural components. And if you look at the improved system, there is no structural damage, only very few non-structural components get damaged. It is very common to show these losses in terms of loss ratio, where we compare the repair cost to the total construction cost. Total cost, where total cost is 1.2 times construction cost, where this 1.2 is the amplification factor to take into account demolition of the building. So here I'm showing the results for the 4 structural systems we looked at 3 hazard levels. And you see that by isolating the structure, your losses get reduced significantly. At the maximum credible earthquake, from 35%, they go to 2%. And you can see that by small investments into your structure, you can save lots of money in case of major earthquakes. Another thing I want to point out, 35% loss ratio is a huge number. ATC suggests that if you reach 40%, that it's not economical to repair your structure, that it's better if you completely destroy or demolish your structure and build a new one. So a special moment resisting frame has a really poor behavior. Next good metrics that can tell you something about the structural system is also business downtime. We want to see how all this damage are going to impact the businesses that we do. And here I'm showing for all these 3 hazard levels and the all systems, I'm showing which ones have a business downtime and how much it is. In blue, I'm showing the special moment resisting frame, and we see here that the displacement, at the DBE level, it has business interruption time of more than a year, which is a lot, and this can cause like huge losses. And at 2% in 50 years, other than having like a special moment resisting frame with a huge amounts of downtime, we also have like a base isolated system, which is based on minimum code requirements, having like around 500 days of the business downtime. And we see that by improving the structural systems a little bit, we avoid having the business downtime, so our buildings are operational and functional immediately, even after the big earthquakes. So to do the total total loss analysis, we need to convert these days into money. And for the downtown Oakland location that we looked at the LoopNet, we found an estimate of $3,550 a day in losses by not being able to rent the space. And if you convert these to dollars, we see even bigger difference in losses when we compare the special moment resisting frame to any other system. So now it goes from 10 millions to maybe $500, something like that. So we see that by small improvements or by small investment, you can achieve a lot. Here I'm just showing the savings of all isolated systems compared to the special moment resisting frame. And here we see that all these 3 improved systems do a really good job, and the code-based design a little bit poorer, but still better than special moment resisting frame. And finally, if you go to insurance companies, what they're interested in are annualized losses. And here I'm showing, again, first the special moment resisting frame, which has about like 70,000, and it drops down to 20,000 for the base isolated minimum code design. And then if you look at the improvements, it really becomes like small compared to the small fraction of the other costs. Another thing the developers want to see is what is the return on investment that they on reinvestment of improving the structural system. And if we assume the inflation rate of 3%, which is shown here, we see that like the return on investment is around 5% and a little bit less for these more expensive improvements. But let's say it's around 5%, which may convince someone to go ahead and do these small improvements. I would say inexpensive improvements and to achieve a lot in terms of losses. Okay, as conclusions, I want to say that all isolated systems have substantially smaller losses than a special moment resisting frame, and the losses are further reduced by improving the isolated system or isolated superstructure beyond the code minimum requirements. Bad thing about special moment resisting frame and base isolated intermediate moment resisting frame that are based on code minimums is that they both have like a considerable amount of downtimes. They lose a function for over a year for a design-based earthquake and more for the maximum credible earthquake. The improved system are fully operational through the lifetime, and the investments in isolated systems is worthwhile. As we saw, that return on investment that they achieve is around 5%. And all we did here, in addition to comparing different structural systems, is also to show how simple PBEE analysis can help in the preliminary stages of design when we select the system that we want to go with. And this provides you a good tool of convincing the developers which system to choose themselves. Okay, that would be all.